Hello. Uh, we're going to begin a new chapter starting today, and it's going to be thermal physics. So, we're going to do heat and thermodynamics. So, the first lecture will be temperature, ideal gas laws, and first law of thermodynamics. So, this lecture slides, I will be doing two videos on this lecture slides, two separate videos on these lecture slides. The first part is the basic part, temperature, thermal energy, the RMS speed of gas atoms, and ideal gas laws. And the second part will be on first law of thermodynamics. And I will, of course, will be making two separate videos on sample problems. First of all, to get started, so we will begin with defining the temperature. So what is temperature? So first, how do we measure the temperature? So traditionally, we measure the temperature using a thermometer, right? And in thermometer, we use a small volume of mercury or alcohol that can expand very quickly, right? The expands or contract when placed in contact with a given object, hot or cold object. The object's temperature then is determined by the height of the liquid column. That's how we measure the temperature. And so there are three very popular, temperature measuring scales. One is Kelvin, Celsius, or centigrade, or Fahrenheit. So these are the three, temperature scales very popular in different contexts. And Celsius and Fahrenheit scales are the most popular scales in everyday life. However, most of the scientific calculations are done in Kelvin or in Celsius, not in Fahrenheit. And the standard unit of temperature, just like the standard unit of length is meters, the standard unit of you know speed is meters per second. Just like that, the standard unit of temperature is Kelvin. And here's the relationship between Celsius and Fahrenheit is given by this equation, and you don't need to memorize that. That will be given. So back to the definition of temperature. So what physical quantity property of the system have you measured? If you measure its temperature, right? So that's the basic understanding. So for example, when you measure the temperature, are you measuring the speed of the particle? Are you measuring the energy of the particle? Are you measuring the pressure of the particle? What actually are you measuring? And the answer is this. So when you measure the temperature of any system, or say a temperature of gas, right, it's the measurement of the average kinetic energy of individual particles, individual atoms, that makes up the gas, right? So this animation shows that actually. So you're basically measuring the average kinetic energy, uh, not the total energy. It's the average kinetic energy of the particles. So here's another animation. So difference in temperature means difference in average kinetic energy, as you can see, right? So this here in this third animation, the particles are vibrating, oscillating with more energy. So each particle will have more average kinetic energy compared to the first one. So obviously this will have more higher temperature. And one more thing, average kinetic energy and the total energy could be completely different. So for example, in the first animation, there are only three particles, but they are moving at very fast rate, very faster rate, very high velocities, right? And that's why it should have high average kinetic energy and so high temperature, because temperature is the measurement of average kinetic energy. Whereas in the second animation, you have lots of particles, lots of atoms or molecules, but they are moving at slower speed, so they have lower, so that's why they have low average kinetic energy, so that means low temperature. But however, if you measure the energy, this one, the left one, has low total energy because it has lot less, significantly less number of particles. But the total energy in the right hand side here is significantly high, but it has low temperature. So the temperature and the total energy of the system could be quite different. And with all this, the formulas we'll be deriving, we'll be using here in thermodynamics are mostly based on kinetic theory of gas, and the kinetic theory of gas relates the microscopic quantities, velocity of atoms, position, etc., to macroscopic properties like pressure, temperature, etc. And the assumptions to derive the kinetic theory of gas is based on two or three basic postulates. It assumes that the n number of identical molecules of mass m are inside the container of volume v. Each acts as a point particle. So you can treat all these gas molecules, right, as a point mass, having similar mass m, identical mass m. The ideal gas atoms do not interact with each other, so that means there's no intermolecular force, intermolecular attraction between these two, individual atoms or molecules. So they don't possess potential energies because there's no intermolecular force. Molecules move randomly and always obey Newton's laws. And collisions with other molecules, they collide with each other and with the walls of the vessel. And all these collisions are elastic based on the kinetic theory of gas, to make it simple. And that creates the pressure. This collision between gas molecules and with the walls of the container, that generates the pressure. So here's the first relationship. We're not going to derive this. We don't have to derive this relationship. But based on the kinetic theory of gas, here's the relationship between temperature and average kinetic energy. So it says temperature, this temperature, big T, should be in Kelvin scale. Temperature is two-thirds of the average kinetic energy divided by this constant called Boltzmann constant. That's what temperature is. Okay, so again, temperature is two-thirds of the average kinetic energy divided by this constant, very small number. This K of B is called Boltzmann constant, and it's 1.38 10 to the power negative 23 joules per K. It's always a constant quantity. And once you have the average kinetic energy, you can find the total thermal energy of the gas. So just multiply by the total number of molecules, total number of atoms, right? So n times this. And then that means the total thermal energy of the system of gas in a container is 3 half mkBT. And in terms of moles, because in many cases moles are more useful, so in terms of moles, small n is represents the moles is 3 half n times r times t, where r is called universal gas constant. And what is mole? So you might have done this in chemistry class or somewhere. One mole has, one mole of any substance has always that many number of basic particles, 6.0023 10 to the power 23 basic particles. So that means number of moles is defined as the total number of particles divided by this Avogadro's number. This is also called Avogadro's number. This shows that this relation clearly shows that the average kinetic energy per atoms depends only on the temperature, not on the mass, right? Not on the atom's mass. You can clearly see. So this is the number of mole definition. So based on that, then based on this formula, right away we can define the absolute zero temperature, right? So based on this, so what happens if the atoms, don't move at all? Say atoms stop moving in a container. So then the average kinetic energy will be zero. Then temperature will be zero, and that's how we define the absolute zero temperature. So absolute zero temperature is the temperature at which all the atoms stop moving, so that the average kinetic energy becomes zero. So the pressure also becomes zero. That's how we define the absolute zero. So absolute zero means, so all the atoms just stop moving, and it's called 0 Kelvin. So 0 degree is the point at which the kinetic energy of the atoms is zero. So no negative below zero temperature is possible in Kelvin scale. The spacing between the divisions of the Kelvin scale and the absolute and the Celsius scale are same, and the relationship between the Celsius centigrade and the Kelvin temperature is this. So the temperature in Kelvin is simply Celsius temperature plus 270. So you just need to add 273 to change into Kelvin. So this is a small lab we could do in a lab. So I'll be assigning this lab. I'll be providing all the data. So this is how you measure the absolute zero. So though we don't have any temperature bath that can go negative 273 degrees Celsius, because based on this, The absolute zero temperature is in terms of Celsius is negative 273 degrees Celsius. That's the minimum temperature any substance can have. You cannot go below that. So how do you measure? So you dip. So you need this pressure measuring device. It has a spherical shell. It's filled with some helium gas, some kind of gas, and you can it is connected to the absolute pressure measuring device. So how we do the absolute zero is just by measuring the pressure of the gas inside this spherical shell at five temperature different temperature bath. So we'll measure at room temperature, we'll measure at liquid nitrogen temperature, which is the coldest temperature we can have in our lab. We'll measure the pressure and temperature at dry ice. We'll measure at boiling water, and then after that you just plot the graph, pressure versus temperature graph, and then by extrapolating this graph you can find the absolute zero. And how do you find the absolute zero? So after plotting this, you can clearly see that they have a pressure and temperature are linearly related, right? Just by doing linear regression, and this is how you find the absolute temperature, absolute zero temperature in lab. And this is a separate part, and then these error bars are for the uncertainties. So uh, today's modern technology has actually achieved a very low temperature, as low as 100 microkelvin, in a device called optical molasses. So they basically do what they do is they slow down the gas molecules, sample of gas molecules, by shining laser light. So the laser light is used to slow down the molecules to almost zero, almost 0 Kelvin. So now next, I'm gonna be showing you a separate, calculation on RMS speed of the gas molecules and its relationship temperature. So here's the relationship. So we're gonna define the RMS speed of gas based on the kinetic theory of gas. So briefly, kinetic theory of gas assumes that all these gas molecules or atoms are acts like a point mass, and they randomly collide with each other with the wall of the vessel to generate the pressure and to generate the total energy. So but in this video, we will be defining the RMS speed of the gas. Okay, so first let's begin with defining the average kinetic energy. So since all these gas molecules for the given gas has identical mass, so each of the gas molecules has mass m. So then by definition of average, so average kinetic energy, which we call K average, is the sum of all the average, so mv1 square plus 1 half mv2 square plus 1 half mv3 square, and so on. There are n number of molecules, say, in this gas cylinder, right? And you don't have to do m1, m2, m3, because all of them is gas molecule has a mass m. They are identical gas molecules. And average, so the sum of the kinetic energy divided by the total number of molecules or atoms, right? That's how we define the average. And now we will try to simplify this by using a summation sign, sigma sign. So 1.5 is common factor, right? And then we put the sigma sign, summation sign, in vi square over n, right? Where vi square is just v1 square plus v2 square plus v3 square, and so on, right? And now we define this quantity, this second term within the parentheses, as vrms square. So that's your average kinetic energy. It's just 1/2 vrms. So what is vrms square? So we just replace this whole thing with vrms square. Vrms square is the sum of the square of the velocities divided by n. And what is vrms? Is the square root of the mean square velocity. So this RMS stands for root mean square speed. So that's the reason it is called root mean square, or in short RMS velocity or speed, because it's the square root of the mean square velocity. So that's why it is called RMS speed. So that's how we define the RMS velocity of any gas based on the kinetic theory of gas. Okay, now next we're going to find the relationship between temperature and average kinetic energy. So relationship between the absolute temperature, big T, and average kinetic energy. And so after long derivation actually from using the kinetic theory of gas, it's a big topic. We're not going to derive this here, but the relationship between temperature and average kinetic energy of the gas for the given gas is given by this relationship. So temperature is 2/3 of the average kinetic energy divided by a constant called Boltzmann constant. Okay, so Kb is called it's a constant quantity called Boltzmann's. It's from the name of the scientist, and it's a universal constant. It's always a constant, and its number is 6.023 10 to the power 23. Okay, so that's the Boltzmann constant number, because I'm sorry, 1.38. I made a mistake here. So Boltzmann constant is 1.23 1.38 10 to the power negative 23. Its unit is standard unit is joules per Kelvin. It's always a constant. Okay. The relationship between temperature and average kinetic energy is given by this formula, and it's based on the kinetic theory of gas. So let's try to simplify that. So temperature, the absolute temperature in Kelvin is 2/3 of average kinetic energy. From our previous definition, average kinetic energy is 1/2 mass the RMS velocity square, and divided by here you still have Boltzmann constant, so 2 will cancel out, and this is good 1/3 of mass times velocity RMS velocity square divided by Boltzmann constant, right? And so then VRMS square will be 3 kb times T over mass, right? And finally the RMS velocity, the root mean square velocity in terms of the temperature is 3 kBT over mass of each gas molecule. This is a very important relationship between the velocity and the temperature. As you can see, for the given gas molecule, the RMS velocity just depends on the temperature, because mass is constant, absolute, this is a Boltzmann constant, it's constant. So based on the kinetic theory of gas and with this data, in the RMS, these are the RMS velocities of different gases at room temperature 20 degrees Celsius. So based on this number, we can explain why Moon doesn't have atmosphere whereas planet Earth has atmosphere. And the reason is this, because if you check the RMS velocity of the gas, our atmosphere is basically nitrogen and oxygen, and its RMS velocity, root mean square velocity, is about 500 meters per second. And the Earth's actually escape velocity is 11,000 meters per second. That means if you want to escape, if a particle wants to escape from its gravitational pull, you need that much speed. Whereas it's much less. It's scale, because at room temperature the air molecules have velocities only 500 meters per second, whereas it needs 11,000 meters per second to escape completely from its gravitational pull, right? But whereas Moon's gravitational pull is very small, so Moon, can't keep the gas molecules because the RMS velocity is, greater than its escape velocity. That's the reason actually Moon doesn't have any atmosphere, whereas Earth does have atmosphere. So here's one more thing. It's called, Maxwell Boltzmann distribution of molecule. If you have a gas molecule, says one type of gas or more than one type of gas molecules in a container cylinder, right? These gas molecules, though it seems to be moving with a random speed, a random velocity, random energy, they follow some rules. They follow some distribution rules. So if you suppose if you measure the speed of this individual particle and plot the histogram, this density graph, this is the molecular speed distribution, right? So it will follow this kind of type of distribution. And as you increase the temperature of gas, the peak shift towards the higher velocity, right, like this. So it will follow this distribution rule, and this distribution rule is called Maxwell-Boltzmann distribution rule. So let me show you a quick look at it in this app using this applet. Here's the applet. So here's the Boltzmann Maxwell-Boltzmann distribution laws. So I just picked the nitrogen gas, and at 300 Kelvin, this is the distribution. So now, if I increase the temperature, right? If I increase the temperature, what's going to happen? So obviously, the peak will shift towards the higher velocity, right? Because more and more molecules will have higher velocity as you increase the temperature, right? And if you keep increasing the temperature, let's see, the peak will continuously shift towards the right side as expected, right? So this is how molecular speed, distribute, and they follow some rules. It's not random. And let's compare at the same temperature. Let's say, go back to say some low temperature, and let's compare. Now this is the molecular distribution for nitrogen, and at the same temperature, let's do distribute for. They have very similar distribution because their molecular mass is almost same, right? About 30. So oxygen and nitrogen gas have this. Whereas if you pick, say, helium gas, it will be lot different distribution, right? Because it's very light. Now, next, let's talk about a very important equation in gas laws. It's called ideal gas law equation, and it has two forms. So you might have actually already seen this formula, in many subjects. Chemistry, if you have done chemistry, it's the same. So any ideal gas has to obey these laws. It's called ideal gas law. So it's called it follows like this. So pressure times volume is equal to number of atoms or molecules, so the Boltzmann constant, and the absolute temperature in Kelvin. So this is called ideal gas law. So where n is the number of molecules or atoms, P is the absolute pressure in pascals, T is the temperature in Kelvin, absolute temperature, Kb is the Boltzmann number constant. And also, second form of ideal gas law equation is in terms of number of molecules and in terms of number of moles. So it says PV is nRT, where n is the number of moles. So R is the universal gas constant. It's always constant, 8.31. So what's number of moles? Not again, number of moles is 1 mole of any substance has that many basic particles. So that's how you define moles. That many basic particles, it could be atoms or molecules, make 1 mole. So that's why the number of moles definition is number of moles is the total number of molecules or atoms divided by this fixed number. It's called Avogadro's number, which is this. Or in terms of molecular mass, in terms of actual mass, so number of moles is the mass in grams divided by its molecular mass. Okay, so that's how you can find the number of moles. So in many problems, you will see expressing the ideal gas law in a number of moles will be a lot easier compared to the number of molecules and Boltzmann constants. So here's an example of the normal moles. All these substances have 1 mole. So this is filled with helium gas. So it's a 1 mole of helium, and this is charcoal, 1 mole of charcoal, one of sugar, one of salt, and copper pellets. 1 mole. But remember, all these they could have completely significantly different volumes and shape and size, but these are all 1 mole. So that means all of them must have exactly same number of basic particles, which is this Avogadro's number, 6.02 10 to the power 23 particles in all these substances, because they have 1 mole, all these substances. So, and you can, to understand this pressure, volume, and temperature, you can do this simulation. And again, here's some link on simulation again. So this ideal gas law, this equation basically says if you keep the temperature constant, right? If you keep the temperature constant, say, and if you try to increase the pressure, volume has to decrease automatically, and vice versa. And if you try to increase the volume, pressure will automatically decrease, right? To keep the temperature constant. And say if you keep the pressure constant and if you try to increase the temperature, the volume has to increase, right? Or vice versa. If you increase the volume, temperature will automatically increase because pressure is constant, and vice versa. So any gas, ideal gases, have to obey these laws. This is the laws for gas.